Welcome back to our EVM from Scratch series. So far, we focused on the stack, the EVM's temporary workspace for calculations. But what happens when you need to store data for longer than a single transaction, or when you need to handle complex data structures? For that, we need to talk about memory and storage. The EVM has two main data locations for storing data. First, there's memory. Memory is temporary, or volatile, as we call it. Think of it like RAM in your computer. It exists only during the execution of a transaction and disappears once the transaction completes. Now, on the other side, we have storage. Storage is persistent. It lives on the blockchain permanently. Think of it like a hard drive. Once you write data to storage, it stays there forever. So why have both? Well, it comes down to trade-offs. Memory is cheap and fast, but temporary. Storage is permanent, but much more expensive to use. Let's look at how memory and storage work in Solidity. Here's a contract called data locations. Notice the state variable myNumber at the top. This lives in storage because it's a state variable. In our function store and return, we first assign a value to myNumber. This uses storage. Then we create a memory array. See the memory keyword? That tells Solidity to create this array in memory, not storage. Finally, we store a value into that memory array. This data will only exist during this function call. When we compile this to EUL, it becomes even clearer. For storing to storage, we use sstore. It takes two parameters, a key and a value. And for storing to memory, we use mstore. This also takes two parameters, an offset, which is the position in memory, and the value we want to store. Notice how the operations map directly to EVM opcodes. Let's explain that next. The EVM has four main opcodes for working with memory and storage. For storage, we have sstore to write data and sload to read data. For memory, we have mstore to write data and mload to read data. Simple, right? But how do they actually work under the hood? Let's visualize them. Memory is organized as a linear array of bytes. Here's what memory looks like, a continuous sequence of slots that we can write to and read from. Each position in memory has an offset. Here's offset 0x80, which is a common starting point for memory operations. Now, let's execute the mstore operation. We're storing the value 42 at offset 0x80. The value 42 is now stored at position 0x80 in memory. Remember, this data is temporary. Once our transaction ends, this memory is wiped clean. Storage works differently. It's organized as a key value store. Think of it like a massive dictionary or hash map. On the left, we have keys. On the right, we have values. Each key maps to exactly one value. Now let's execute sstore with key 0 and value 42. The key is 0 and the value is 42. The EVM creates this mapping in storage. This data is now permanently written to the blockchain. It will persist across transactions, blocks, and even years. That permanence comes at a cost, though. Storage operations are among the most expensive operations in the EVM. Let's recap what we've learned. Memory is volatile and cheap. Use it for temporary data that only needs to exist during a transaction. Storage is persistent and expensive. Use it only for data that absolutely needs to live on the blockchain permanently. Understanding when to use each one is crucial for writing efficient smart contracts. In our next video, we're going to explore control flow and learn how the EVM handles jumps and conditional logic. Thanks for watching. If you found this helpful, hit that like button, subscribe for more EVM content, and let me know in the comments what you'd like to learn next. See you in the next one.